Hello everyone, and welcome. I have a request from one of my viewers on the video about how to measure inductance with an oscilloscope, whether or not we could use a tuned circuit and do the same thing, and the answer is yes, we certainly can. And the way that we would do that is we have a pulse coming into this circuit, which consists of a capacitor here decoupling and a little bit of isolation from the generator, and an unknown inductor here, and the capacitor that we do know the value of. And then on this side of the circuit is connected to your oscilloscope with your scope probe on ×10. That's important. We'll explain that later. And so basically, when you hit any a resonant circuit like this with a pulse with some energy, it will naturally ring or oscillate at its resonant frequency. And so you can take that waveform on your oscilloscope and measure the frequency of it, either by measuring the time for one cycle and doing the math for that, or with the newer scopes, you're able to actually just have it measure it by either using the cursors on the scope. There's cursors where you can do that, and it'll give you all the data associated with those cursor positions. And in the case of my scope, I'm using a Rigel DS1102 for this, and there's a measure button, and when you press that and press display, it'll display all the characteristics of that waveform, including the frequency, which is what I'm going to do. You can narrow that down with the scope to whatever specifics you want, but it was in this case just as easy to do that. And the waveform looked a little nicer than the one I drew on the paper here. Hi. Okay, let's see what else here. Now the inductor I used was a 0.86 microhenries. I'm pretty sure that value because I pulled it off of an old Heathkit board, and I looked up the part values on the schematic before I pulled them and labeled them, so I would have that. Now I had to pull a couple turns off of it in order for it to fit in the board, so even though I know it's around 0.86 microhenries, after pulling a couple of the turns off, it's not going to be right. It's going to be something less than that. And I went online. There's a calculator for determining the inductance using toroids, and which is what this coil is in my case. My inductor is a toroid. And you can calculate the approximate inductance, and so I put in a certain core, and I put in the value. It gave me the number of turns, and then I took took 2 turns off and come up with this value here, this 0.81 microhenry. So when we do all this, it should come up to approximately that. Now keep in mind, is all this to some degree is an approximation, but it'll definitely get you in the ballpark. And then the formulas you use for that are going to be, well, the formula for resonant frequency, which is 1 over 2 pi square root of LC, which would be the inductor and the capacitor. And then you can solve that for L, which is 1 over 2 pi F squared times C. It's much easier to use an app or a web page that has a calculator on it, unless you really feel inclined to actually do the math. That's fine too, of course. So that's kind of what we have for the setup and what we're going to do. And then at the end, I'm going to take the scope probe scenario and go from from ×10 to ×1, and let you see the effects on the resonant frequency of the ringing, the oscillation. The reason it does that is because, I mean, you've got a probe with a series capacitor. Actually, that's to our benefit, weirdly enough. But on the input of the scope, there's usually a capacitor to ground and some impedance. I'm not sure if it's an actual resistor value or not, but I think mine is. It is 1 megohm actually. I just looked at the scope, but it's 15 picofarad on mine. And then whatever length this cable is, it's a shielded cable, so there's going to be a capacitance per foot on that cable to ground, which is also going to, in effect, through the series resistor, if you have one in your probe, going to be in parallel like I've drawn here with the tank circuit. And of course, the more capacitance you add to this tank circuit, in the case of it being a parallel tank circuit, the frequency is going to drop. Drop, that's correct. So that's an important consideration as well, and I'm hoping to show you that. And the other thing I'd like to show you is the effects, not the effects really, show you how it looks on the spectrum analyzer, because when you look at the waveform you go, well, that's a nice, it's a ringing waveform like it should be, but it's an oscillation, it's a sine wave. You would think it'd be pretty clean. Maybe not so much, but we'll see that. And okay, so that's that. So I'll go ahead and show you the equipment and what we've got set up, and we'll go from there. Alright, so this is our test circuit. And we've got this is our inductor here, and we're not sure exactly what that value is, but it's close to 0.86. We're just not sure where, after taking a couple turns off. And behind this probe there's a cap here. That's our parallel capacitor, the 290 puff or picofarad. And this one here is a decoupling and kind of helping to isolate the generator, the effects of the generator from the circuit. And these two here, they're just they're not functional, they're just in there so I have leads to clip to basically. So that's our circuit. Alright, so here's the function generator setup. Again, it's a Rigel DG 4162. This is not overly critical, and you can adjust these parameters, particularly the frequency and pulse width, if in the leading edge time, if you have a generator that can do that. If you're just using a pulse generator that you built, it just generates a pulse of a fixed width and frequency and so on. And it'll probably still work. Might get some different looking waveforms, but you'll still be able to measure the frequency. Anyway, so in this case we've got a frequency set to 600 kilohertz and 4 volts peak to peak, no offset, and anyway, the rest of it's like pulse width, and I think the duty cycle was like 10% until I started playing with the pulse width instead. But it was just to make the ringing waveform on the oscilloscope look like a nice, clean looking ringing waveform. So that's the tracking generator setup. Alright, now here's the oscilloscope with the ringing waveform on it. And you can see when you're looking at the left edge part of the screen, the amplitude is greater, and then it slowly goes down because it's getting hit with the pulse energy here, causing it to oscillate, and then the pulse is removed because the duty cycle is such that it's on just a short duration and off for a longer duration, and so that oscillation is slowly dying out, and then it starts over on the next pulse over on this side. Now with this scope, you got a couple of options here. You can just hit the measure button, and down at the bottom says display all. You can do that and you get all the parameters on the bottom. I like that feature most of the time, unless you need more room on the display for your waveform or what have you. And then the other thing you can do, if you turn that off, you can also it's not display, my bad, it's measure, and then you have choices between which channel for the source, voltage or time. And so if you wanted to, you could just click time, because frequency is a function of time, and you can move it down to frequency and select that item, and it'll put the frequency down at the bottom. You can also do it that way. It really is up to you. Now it's showing a frequency of 10.42 megahertz. It toggles, actually it's been toggling between that and most of the time between that and 10.87, which it just did. The scope I don't think is meant to be that accurate as a frequency counter. I don't think it's meant to be a frequency counter, but to kind of get you in the ballpark. Now the other option you have, I'm really not going to do it, but you can also, if you want to spread this waveform out, as long as I can keep it, there we go, locked trigger wise, we can select cursors and turn them on.
K2.
Sorry about that.
LL repeater.
And keep okay. And you can, anyway, go through the cursors. You can move the cursors over and actually measure it, and it'll tell you what frequency as well, as long as you just measure the time for one complete cycle. I've done that too, and it comes out exactly the same as the display had earlier, so it doesn't really matter to me. Anyway, so I'm going to go back to, oops, not cursor, my bad. I'm going to turn, oh, now the cursor's are on. That is not what I wanted to do. Let's turn that off. There we go. And go back to display. I keep doing that, don't I? Measure and clear, to clear that one that I did individually. And go back to display. You know, I'll never get that right, will I? And turn them all on. There you go. So they're all back. And again, it's like I said, a toggling between 10.42 and 10.87 megahertz. So we can take that information, go back to a calculator, whether it be online. I found several for my tablet, which works out really well, and one I really like actually, where you can tell it which one you want to solve for and plug in the other two values, and it gives you that. So let's go back to that, and we'll do those calculations and see what we get for a value, and then we'll show you the scope probe effects. Alright, just having an amazingly fun time trying to get this to focus. I'm not sure how well you can see this, but as good as I can get it, it's the closest you're going to get to seeing me, maybe, too. Sorry, couldn't resist that. Okay, but it's a nice calculator. Up on top, it's got find frequency, find inductance, and find capacitance. You plug the numbers in, and away you go. So, going to go to the first one, and make sure it's in megahertz. And I'm going to enter a number into there of 10.87, I think is what it said, megahertz. And oh, I'm on find capacity, and I don't want to do that, so I want to do find inductance. So we'll have to, whenever you do that, by the way, you switch these, you have to start over with the data that you're entering. So again, to megahertz, 10.87, and then down to the bottom one, which is in the units of picofarads. It's a very good calculator, very intuitive. You don't really have to say, how do you use this thing? 290 picofarads. And as you're putting it in, it's actually calculating the value up on top. So that gave us an equivalent of 0.74 microhenries, which is less than the 0.86, the original. Well, let's take the frequency now, because like I said, don't overly trust the scope. Let's try the other one they gave us, 10.42, and that comes out to 0.804. I think it was what I went with, actually. That's why I said it was approximately 0.81. So anyway, that's all really very close if you think about it, trying to calculate an inductor anyway. So yeah, it works out good. So it's a good calculator. It's really easy to use, very intuitive. So well, we got all that. So now the next thing I'm going to show you is what happens when you change the scope probe from times 10 to times 1. Okay, so now what we're looking at on the spectrum analyzer right now actually is it's a video average of the content of that ringing waveform at the older frequency, the 10.42. Again, I was just showing you this to show you that there are still, a bunch of different frequencies in there, that the waveform's not really all that clean. Just found it interesting, that's all. Not really relevant to what we're doing. So we're going to go to trace, turn video averaging off, go back to a waveform that's actually real time kind of a thing. Right, so what I want to do now, I just want you to watch. I'm going to change the probe again. Now right now it's on times 1, and the peak table, by the way, just so I look at it, the peak table is showing the highest amplitude waveform is around 8.99 megahertz, so that's fairly close to the other one. Alright, so let's put it into times 10 and watch them shift. Did you see the peak shift? They went from left to right, showing that the resonant frequency shifted because the peaks that are higher now are over to the right, and number 4 is the highest peak, and that's at 10.799 megahertz or 10.8 megahertz. So this is a good way to visually see that the resonant frequency is actually shifting from, in this case, lower to higher, because I went from times 1, which adds more capacitance, to times 10, which removes some of that capacitance, and that's in parallel with that capacitor in the parallel tank circuit. Alright, so what we've learned today is that we can take a tuned circuit, like the parallel resonant circuit here, with an unknown inductor, energize that circuit with a short duration pulse, cause a ringing oscillation at the resonant frequency, and measure that frequency, and then use your formulas or your app or website, whatever, to calculate the inductance. So thanks for watching, everyone. Comments and shares and likes are always appreciated. And if you have any other ideas or suggestions for videos or questions about this one, feel free to ask down in the comments section. Thanks a lot, and see you again. 7-3 for now.